So I want to talk about capacitance. Capacitance is a word when you're talking about circuits or charge and all that. It's the ability to store charge. How much charge can a capacitor, it doesn't necessarily have to be a capacitor, but how much charge can be stored on an object for a given voltage? So capacitance, and I hate to tell you this, but we use the letter C, is equal to Q over V, or is defined as Q over V. So it's the charge per unit voltage. Given a sphere, if I place a certain amount of voltage on it, how much charge appears on it? Okay, it's the ratio of charge to voltage. It's measured, obviously, it's coulombs. I'll write that out. Coulombs per volt. That's the unit of capacitance, the SI unit. That has another name, named after Michael Faraday. It's a farad. It has the SI symbol, capital Z, no, F. Okay, capital F for farad. Everyday capacitors, like probably in your phone, your cell phone, you have maybe 5 billion capacitors. I mean, it's in the billions anyway of capacitors. Capacitors are ubiquitous in electronics. They do a lot more than just store charge. We'll talk about some of that stuff in lab this week, and next week we're going to do the RC circuit, which is a resistor and capacitor together. So these capacitors are everywhere. Everyday capacitors, usually in the microfarad range, picofarad, nanofarad, something like that. A farad is a pretty large amount of capacitance. And we're going to find out that this capacitance depends on the object. It really doesn't depend on the charge or the voltage. It's a ratio. It depends on the geometry of the object, the materials the object are made with. When I say object, the capacitor, whatever you're measuring the capacitance of. It's just like we saw in the lab with the resistor. The resistor is a ratio of voltage to current, that's resistance. But the resistance ends up just depending on the material, the length, the area, some other factors possibly, temperature, all that stuff. This is the same idea. So I'll look at the maybe the simplest version of a capacitor. So a parallel plate cap. A parallel plate is two conductors separated by some distance d, some little distance d. So it's sort of like this. You got one plate, and then another plate, and they're separated by some little, you draw that this way. They're separated by some little distance d. That's little d, and they have an area A. Okay? Put a power, somehow you deposit charge on the plates. I'll connect it up to a battery, let's say. So here's a battery. What the battery does is it starts moving charge from one plate to the other. So you get I'll tell you this in a second, you get an electric field. They're close enough that you get a field between the two, and the battery starts doing work. It moves charge from one plate to the other, and this plate, since the way I've drawn it, this plate gets positively charged, and this plate gets negatively charged. Then when there's enough electric field between the plates, because you got positive over here, negative over here, you get an electric field. When the electric field times the distance is equal to V, it's all stop. The battery can't do any more work against that electric field. It doesn't have the potential to move any more charge. Okay? So if I draw it end on, or edge on, here's plus, I don't know, how many pluses do I need? Here's minus, okay, this is that little separation distance D. So I'm looking edge on, and due to this separation of charge, there's an electric field in this direction. Okay. All throughout the plate, or between the plates. Okay, that's E. The energy that is stored in, I mean, these things store energy. There's charge on them, but there's energy stored in the capacitor. That energy is stored, we say that it's stored in the electric field. The electric field is where the energy resides, all right? The charge separation is, you know, a bunch of electrons over here and the absence of electrons on this side, okay? And that energy is stored in the electric field. So since I charged it up with this battery of voltage V, V is equal to ED. Okay, Ed. Not worried about the negative. I mean, the potential difference, you're going down in potential this way, you're going up in potential this way. So this is the high side, this is the low side. If that's sort of engineering parlance, but that's high and low. Okay. Let's see if we can calculate or get an idea of what the electric field is, the value of the electric field in between the plates. I normally would do this when we were talking about Gauss's law, but I didn't do it, so I'm going to do it now. So I'm going to insert a Gaussian cylinder inside the cap. Okay? So it's a little finite closed cylinder. And call this area A1. This is not this area, okay? That's why I'm calling it A1. What goes better on capacitors than A1? I don't know. All right. Really bad joke. Here's the setup, my logic. I claim that out here, E is equal to 0. Reason. This separation distance D is very, very small. And I can be sort of as far away as I want to with my Gaussian cylinder here. Okay? So you get an electric field this way from the positive plate, you get an electric field this way from the negative plate, and they cancel one another out there. I can also think about it like, you know, when we did this thing of calculating the electric field due to this infinite sheet of charge. Do you remember the result that we got for that? When we had this big, you got this big area of charge and the electric field, let's say it's positively charged everywhere. The electric field was equal to sigma over 2 epsilon naught, right? Remember that? And it was a constant everywhere. So I'm imagining that these plates are very, very large. I'm out here. You've got a constant field this way from the negative plate, a constant field this way from the positive plate. They cancel. All right. Let's do Gauss's law. No contribution to this end. There's no field out there. There's no contribution to the flux through the cylindrical part because the field is parallel to the cylindrical part here. The only contribution to the flux is from that little end, A1. So E times A1 is equal to Q enclosed in the little cylinder over epsilon naught. Well, Q enclosed is sigma A1 over epsilon naught. So A1 cancels, and you get E inside the capacitor is sigma over epsilon naught. Makes perfect sense. It's just the field from the positive is sigma over 2 epsilon naught. The field from the negative is sigma over 2 epsilon naught in the same direction. The total field is sigma over epsilon naught between the plates. Okay? C is equal to Q over, I'm going to go over here. C is equal to Q over V. That's the capacitance is equal to Q over V. So C is equal to Q over V. V is equal to ED. So Q over Ed. But E is equal to sigma over epsilon naught. So you get Q, I keep wanting to write sigma everywhere. Q, sigma over epsilon naught. Yeah, epsilon naught. Then you get a sigma down here and a little d. Did I do that right? Yeah. Okay. But Q, the total charge on this thing, is equal to sigma A. Yeah? That's the charge density times the total area. And this Q, by the way, that we're talking about, is the charge on one plate. The net charge on the entire capacitor is 0. You got an equal amount of positive and negative. So we're talking about typically the positive charge on one plate. Making that substitution, I'll go up here, and you get sigma A epsilon naught over sigma little d, and that's equal to the capacitance. Sigma cancels, and you get the capacitance is equal to epsilon naught A over little d, and that's it. That's the capacitance of a parallel plate capacitor.
And that's on the positive side.
Oh, that's the capacitance. Yeah, it's just a number that represents this. If I know the capacitance and I have a particular amount of voltage, you multiply and you get the amount of charge stored on the cap. Okay? So like I mentioned earlier, the capacitance is a function of the area, the separation distance, and of course you have epsilon naught in there to make this work out in farads. All right. Let's do a calculation. So let's say that I want to build a 1 farad parallel plate capacitor. So C is equal to 1.0 farad. I'll have the plates pretty close together. I'm going to make them a millimeter apart. So I want a 1 farad capacitor. The plates are a millimeter apart. I need to know how much area I need to build my cap. Epsilon naught, I'll just remind you, is 8.854 times 10 to the negative 12 coulombs squared, that's coulombs, per Newton meter squared. Okay. So I'm going to solve for the area. So the area is equal to the capacitance is 1.0 farad times the separation distance, which is 1 times 10 to the negative 3 meters, divided by epsilon naught, 8.85, that's not a point, that's okay, times 10 to the negative 12 coulomb squared per Newton meter squared. Can somebody please calculate this? So 1/8 is about 0.125. 1.1, I don't know, something.
1.13 times 10 to the 8.
Yeah. 1.13 times 10 to the 8 square meters. Is that big? 113 million square meters. Let's put it in something a little bit more tangible. Football fields. How many football fields would I need? 1 football field. What's the area of a football field? Well, how long is a football field? 100 yards. That's about 100 meters. How wide is a football field? I think it's about 50 yards, 55 yards. So we'll say 50 meters. You can look it up. Somebody who's a football fan in here. I think it's about 100 yards by 55 yards. So I'm going to say 5,000 square meters. So how many football fields do we need? Give me the more exact number. 22,500 football fields. Okay, that's still, does that make it better? I don't know. Okay. Are there 22,000 football fields in the U.S.? Probably.
How many square meters
Yes.
is there?
The area of the football field is 7,140 square meters.
What? How's that? They must be counting the end zones
I'm guessing so.
and the sidelines and everything.
16,142.
What?
16,142.
What?
According to that number.
Oh, okay. So according to that number, you'd need 16,000 football fields. Anyway, it's an enormous amount of area. And when I took this class like a million years ago, everybody would, I think it was Dr. Holmes. He said, there's no way you could build a 1 farad capacitor. It is take so much area, even though you could get the plates really, really close. Because look at the equation. If you can decrease little d, you can increase the capacitance, okay? Here I have a 1 farad capacitor. Amazing technology. Yeah, there's 22,500 little football fields in here. Okay, yeah. Um, these are really cleverly made. Some clever scientist, engineer, whatever they were, figured out how to make these so-called, these are called supercaps. Back in the old days, when you bought a computer, on the motherboard there was typically a battery. And the battery was soldered into the motherboard, and that was there to keep all your information, keep power on the chips for all the startup stuff and everything. Nowadays, it's one of these little supercaps. Because these store energy, and you charge it up, and you've got whatever voltage you have across it, and you can reuse that. Sort of, it's not a battery, but it's the same idea. You have a power source there, all right, and it decays. We're going to talk about the decay in lab, the RC circuit. Because the old batteries would, just like any battery, they get old, they don't work anymore, they leak, they ruin the computer and all that good stuff. So the way these work, maybe these were developed 20 years ago, 30. I think the idea has been around a long time, but the ability to manufacture these things has not been around for maybe about 20 years, maybe not even that long. You ever heard of Dr. Scholl's odor-eating inserts? Yeah. They advertise these things you put in your shoes and they eat odor. Do you happen to know how those work? It has something to do with this supercap. Do you know the material that's inside the odor-eating insert that eats odor? What? No? Okay. Well, I don't know. It's usually what they call activated charcoal. If you look at the surface of charcoal, which is like a carbon, burned carbon, hydrocarbon, it would look under the microscope, it's got all these little spaces and little crevices for things to hide. Okay, so that's the outside, there's the inside. So it's an enormous amount of surface area in a small space. And these bacteria that are floating around from your feet, bacteria gets trapped in these little spaces. Okay, and then eventually, they stop working because they get full. All right. Lots of things have activated charcoal filters, and that's how they work. Material comes through there and it gets trapped in all these little spaces. But that's an enormous amount of area. Okay? And that's the way these supercaps, there's more to it, but that's part of how they work. They take that area or that material and scrunch it up. So, try to draw it. So, I don't know, a couple of things. Okay. So there's a little bit of it. And they metal coat it on each side. And it's very, very thin. So they coat it with some maybe nickel or silver on each side. So the spacing between the plates, it's not like a plate, like a parallel plate, but the spacing between them is very, very small, and you get an enormous amount of area packed into this little space. So they scrunch it down into this little space. But the downside is it's very low voltage. This is a 5 volt, Because what's going to happen if like we talked about with resistors, you have a resistance value, a tolerance, and then you have a value for, how much current do you want to put through it? How much power do you want to dissipate in the resistor? You can't just put any amount of current, it'll burn the resistor up. Same idea here. If you go over a particular voltage, depending on the way the cap's manufactured, if you go over a particular voltage, what's going to happen? You're going to get a field that's large enough for the charge to jump the gap, just like a spark. Okay, and that's when the capacitor goes pow. All right? Yeah, charge makes it through one little place, and once that dam is broken, then all the charge just rushes through, and you get a big spark, and the cap blows up, and smoke comes out, and all that stuff. So you always have a voltage rating on caps. This is rated at 5.5 volts, so that means that you can, any voltage between 0 and 5.5 is fine, plus it's an so-called electrolytic cap. It depends on the polarity as well. This is the negative side, that's the positive, so you can't really see the leads very well, but there's two little leads down here. When you hook the negative to this side and the positive to that side. If you hook it in reverse, pow, okay. So that's the kind of caps we're going to use in lab. We're going to have electrolytic caps, and if you hook them up the reverse polarity, it's bad. Okay. So yeah, we've got 1 farad. I had another one around here. I don't know, somebody may have stolen it, but maybe it's in my little car down here. No. Anyway, there are all kinds of geometries and materials and dielectrics, which we'll talk about, that you can increase the capacitance of your capacitor with. Okay. That's the simplest. Epsilon naught A over little d. Any questions about that? Another way that they make fairly, well, it's not huge capacitance, but they take a film like foil. I'll have a foil, and it'll be very, very long. There's also a dielectric, but they take a foil, it's really, really close, and then they just roll it up and stick it in a cap. Okay. Well, those are spiral wound capacitors and so forth. They're wrapped. All right, so back to this equation for capacitance. C. I'm not going to use the defined as, I'm just going to put Q over V. Okay. Like we always do, there's, 3 variables. You know 2 of the variables, you can find the third one. So in a circuit, here's about as simple as you can get. By the way, I'm drawing these, let's say V is equal to 12 volts, and this is equal to 3 microfarads. In any circuit, even though I'm not drawing it in, there is resistance present, okay? Except if you want to go into some exotic superconductors and things, but there's resistance present. Find the charge on the capacitor. Q is equal to C times V, so that's 3 times 10 to the negative 6 farad. Couldn't remember there for a second. Times 12 volts, and that is equal to 36 microcoulombs. Okay. That C stands for coulombs. This is what we're going to do. Let's look at capacitors, combinations of capacitors, just like we did with resistors. For combinations of capacitors, I'll look at parallel first. Caps in parallel. The connection, when you say parallel, that is the connection, okay? Here's plus minus V, here's C1. Caps are always drawn as two little parallel lines of the same length. A DC power supply or battery are two parallel lines of different lengths, where the longer line is positive and the shorter line is negative. That's pretty standard notation. Caps in parallel have equal voltage, just like resistors in parallel. And the equivalent capacitance, already erased. For the parallel plate, C is equal to epsilon naught A over little d. It's like adding area. It's like just adding area when you add two caps together in parallel, or 3 or 4 or whatever it is. You just add them up. C equivalent is equal to C1 plus C2 plus dot, dot, dot. Capacitors in parallel add up like resistors in series. They're opposites. They have equal charge, they have equal voltage, and this, if C1's larger than C2, it gets more charge than C2. Series, the connection is just like resistors. You have one common connection between the two. Okay. Caps in series have equal charge. Whatever the charge is on C1, if they're in series, you're guaranteed that's the same amount of charge as there is on C2. One way to think about this is, look at this connection between the two. There is no physical connection between the battery and this wire and this plate and this plate. So whatever charge is separated between the two, like this side gets positively charged, this side gets negatively charged due to the presence of the positive charge. Well, it had to pull that negative charge over from this plate. This plate has a net positive charge, and then this plate gets a negative charge. By conservation of charge, whatever negative charge came over here, you get an equal amount of positive charge here. There's nowhere else for it to go. Okay, so both caps have the same amount of charge. Doesn't matter what the capacitance is if they're in series. Now, one of them's going to have a higher voltage. The smaller cap will have the higher voltage because you need more voltage to put that amount of charge, whatever it may be, on the smaller cap. And they add up just like resistors in parallel. So 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus dot, 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 as many as you have in series. And you can solve this. I like to use this. C equivalent is equal to C1, C2 over C1 plus C2. So if you can remember series and equivalent for resistors, you just do the opposite for caps. Okay. So what we're going to do is we're going to look at some combinations of capacitors, series, parallel, figure out how to analyze the circuit and work through the circuit and find all the charge and voltage on all of the caps. Okay. Example. Here's that circuit that I had in lab with the light bulbs, but I'm going to use capacitors. And I can draw it all kinds of weird ways. Plus, minus, I'm going to make this 15 volts, 3 microfarad. I'll use odd numbers today. 5 microfarads and 7 microfarads. Okay. So the idea is to reduce the circuit down and find an equivalent capacitance for the whole thing, and then work backwards and find the charge and the voltage on each one of the caps. That's the recipe. Okay. Where do I start? I'm looking for things in parallel and in series. Will?
Start with parallel.
Yeah, which ones are in parallel?
5 and 7.
Yeah, the 5 and the 7 are definitely in parallel. I drew it very descriptively. Okay. Yeah, the 5 and the 7 are in parallel, so I'm going to draw the next picture with that equivalent capacitance. So it would look like this. This is 3, and this is 12. All right, just add them up if they're in parallel. Following that? Now, the 3 and the 12 are in series. I think that's sort of obvious. 3 and the 12 are in series. So I'm going to draw another picture. I highly recommend drawing all these pictures step by step. Maybe you're good enough where you don't need to, but I need to. So that is, what is that, 36 over 15. So 12 over 5.
2.4.
Okay, 2.4. Well, that's it. We got it down to one equivalent capacitance. Now I can find the charge stored in the circuit. So if I know the capacitance and the voltage, C times V, I mean I can move this around, CV equals Q. C times V is equal to the charge. So 36 microcoulombs. This times this. Yes, okay. All right. This equivalent capacitance came from a series connection. Whatever charge you find on an equivalent capacitance that came from series, that charge is on each of your series capacitors. They have equal charge. So this has 36 microcoulombs, and this has 36 microcoulombs as well. Now that I know the charge and the capacitance, I can find the voltage. Because solving for that, it's charge divided by capacitance. V is equal to Q over C. Okay. Voltage here, 12 volts, right? Q over C. Well, whatever's left over, I haven't talked about conservation of voltage around a circuit, but whatever's left over has to be on here. So it's Q over C. That's 3 volts. Okay, we're done with this one. We know the charge, the voltage. This is 36 microcoulombs. This is 12 volts. This equivalent capacitance came from a parallel capacitance, okay? They must have equal voltage. So this has 3 volts, and this has 3 volts. because came from parallel. Charge is equal to capacitance times voltage. This has 15 microcoulombs. Whatever's left over, this is what, 21? 3 times 7, 21 microcoulombs. That's it. We know all the charge and all the voltage on each cap. This is that kind of recipe thing I was talking about. We'll start with a circuit, reduce till you get to an equivalent capacitance, then work backwards, find the voltages and the charge. By the way, in this case, you can see that the larger cap, when they're in parallel, the larger cap has the larger charge. They have equal voltage, and so the larger cap gets more charge. In this case, where it was series, they have equal charge, so the smaller cap needs more voltage to have that amount of charge on it. So in series, the smaller cap will always have the higher voltage. In parallel, the larger cap will always have the higher charge. Okay. Are there any questions on this little plan? I won't say it's simple, but it's straightforward, and you practice a little bit with it, you get really fast, you can do these things quickly. Okay, I'll see you.